So today we're going to do more differential equations. We're doing that for the rest of the semester. Our main topic today is the idea of something called a slope field. Slope fields are a pretty cool idea, but to try to make them by hand is difficult. Let's start off simply. Differential equation, or ODE. ODE means ordinary differential equation. We did applications on Wednesday, free fall and population growth. Today, we're not going to do any applications. We'll go back to applications next week, especially starting Wednesday and then on next Friday as well. I could say more about this differential equation. First of all, it's going to be what's called the first order differential equation because I'm only going to involve a first derivative of an unknown function. A second order differential equation would also involve a second derivative. dy dt equals, let's make it be fairly simple, say t squared minus 1. So the right-hand side of this differential equation only depends on t, the independent variable, not y, the dependent variable. We encountered a problem like this on Wednesday with the free fall. It was a constant negative g at first when we integrated once to find the velocity. Then it was negative gt plus a constant to integrate again to find the height. It's called a pure antiderivative problem. Pure antiderivative problem, and it really is the easiest kind of differential equation because it is equivalent to an antiderivative problem. You can solve it just by integration. In fact, you could say it's equivalent to this problem, y equals the integral, the indefinite integral of t squared minus 1. Why are those equivalent? They're just two different ways of saying the exact same thing. In both cases, you're after an antiderivative of t squared minus 1. Here, we're using indefinite integral notation. Here, we're saying, find a function. Y is a function of t. That's understood, by the way. When you write dy dt here, it's understood that y is a function of t. A function whose derivative is always t squared minus 1. That would be an antiderivative of t squared minus 1. So these mean the same thing. Two different ways of writing the exact same thing. And you just do the integral to solve it and get 1/3 t cubed minus t plus c. Whereas with indefinite integrals, c is an arbitrary constant. Arbitrary constant. It can be anything. The equation y equals 1/3 t cubed minus t plus c is called a general solution. That actually means two things. When something is a general solution, it means, first of all, it is a solution, no matter what c is. That's the first thing it means. Second thing it means is that all solutions look like that for some c. Those are two different things. Say it again. This is a solution no matter what c is. And all solutions can be put in this form. They can be made to look like this. I am calling it a general solution. It's in general, when you write general solutions, there's not necessarily a unique way to write them. This is pretty well a unique way to write the answer. It's hard to imagine writing it any differently. I mean, you could call the constant something different, but conceptually speaking, it's still the same idea. Let us once again check that it's a solution. With pure antiderivative problems, checking is super easy. Just differentiate and see if you get the right-hand side. The left-hand side of the differential equation, LHS, is dy dt. I need to substitute this function into that, meaning I need to find its derivative. And it gives me t squared minus 1, which is the right-hand side for all t. It's almost too easy. There's some things that are too easy that they feel confusing. Like, did I really do it? Yeah, you did. There's nothing much going on here. Pure antiderivative problems are pretty simple. It's when you get to non-pure antiderivative, when you get to non-pure, I shouldn't even call it an antiderivative problem. When you get to other differential equations that involve y on the right side, that things get more complicated. Both for solving the differential equation and even for checking the solution or the proposed solution. Since C is an arbitrary constant, think about what happens when you add a constant to a function. What happens to its graph? It's a vertical translation up or down. Adding a positive constant translates the graph upward. Adding a negative constant, which means subtracting a positive number, translates the graph downward. So what this is really saying is, because we've got this plus C for our arbitrary constant here, is that all solutions are vertical translations of each other. So all solutions are vertical translations of each other. And that's going to happen with any pure antiderivative problem, where the right-hand side only depends on the independent variable t. But we saw an example on Wednesday, a couple examples, in fact, where the right-hand side only depended on the dependent variable. For our example on Wednesday, we called that p, the population. K times p, that was the exponential model. And then the logistic model that we did was, the right-hand side was, I think, was p times, in parentheses, 1000 minus p. But it depended on p, the dependent variable for the function. Those were not pure antiderivative problems. It was not clear what the solutions would be. In fact, we had to use Mathematica, desolve value, to find the solution for the logistical one. For the exponential one, we did guess an exponential function. Before I draw the slope field, we should also think about initial value problems. An initial value problem, or IVP for short. Anytime I say IVP in this class, it means initial value problem. Is not just a differential equation, but also an initial condition. I could take this same differential equation, write it down here, dy dt equals t squared minus 1, and then I can add an initial condition. For example, y of 0 equals 1. Whereas differential equations typically have infinitely many solutions, right? C can be anything. This is really a one parameter family of solutions. It's a family of functions that are all vertical translations of each other. An initial value problem like this typically only has one solution, a unique solution. How do you find it? Use the general solution, or a general solution. In our case, that's fairly easy. What does this initial condition say? It says y equals 1 when t equals 0. I am abusing notation a bit here, which is pretty standard to do in differential equations. When I write y of 0, it's like I'm treating the letter y as both a variable and a function name. Y is the dependent variable for the solution. But by writing y of 0, it's like I'm treating it like a function name too. That's technically not a good thing, but we live with it. Actually, some next week I will introduce a new kind of notation that is a little confusing, but we'll try to dispel with that ambiguity there. So use the general solution here, replace y with 1 and t with 0. 1 will have to equal 1/3 times 0 cubed minus 0 plus c, which does equal c. So c does equal the initial condition. That is happening here as it happened on Wednesday with the free fall example and the exponential growth, but it does not happen in general. In general, c is not the same as the initial condition, though you can use the initial condition to solve for c. They won't typically be equal though. Here they are. And so I can say that y equals 1/3 t cubed minus t plus c, where c is 1. That is a single function. This is the unique solution of the IVP. It's actually kind of similar to difference equations, recurrence relations that we talked about with sequences, where you had like a recursive equation, xn equals 2 times xn minus 1. There are infinitely many sequences that satisfy that recurrence relation, but once you give the initial condition, x sub 0 or x sub 1, then the sequence is specified. It's very similar to that. Of course, we can graph these solutions. There's no problem graphing functions like this. But I want to do more than just graph solutions. I want to graph something called the slope field. That's our main thing to do today, is the idea of a slope field. Why? And what is a slope field? I haven't said what a slope field is. A slope field, big picture wise, without getting into nitty-gritty details here, is going to be a picture in the plane of a bunch of little line segments, that solution curves are going to have to follow, you might say. Like the line segments tell the solutions which directions to travel in, is the big picture idea of what a slope field is. Why is that good? Well, for one thing, it can be automated, like with Mathematica. You can make the slope field pretty quickly. You can draw solutions pretty quickly. More importantly, they can help you see what solutions look like for harder examples than this, where the right-hand side maybe is some complicated function of y, or maybe even some expression that involves both t and y. Do such nightmares exist? Yes, they do. Are they important? Yes, they are. We'll even see applications where the right-hand side depends on both t and y. And some of those examples, Mathematica won't even be able to solve them. D-solve value won't be of any use. You'll have to look at the picture and trust the picture. But what is a slope field? What is a slope field? Here's the idea of a slope field. A slope field for a first order differential equation, diffie-q, not second order or third order or fourth order, first order. You only have a first derivative, not a second derivative, not a third derivative, etc. Of the form dy dt equals some expression on the right-hand side involving both t and y in general. Some expression involving both t and y in general, but in particular examples, it might just involve t or it might just involve y. is what? Let's give a name to this expression. If it only involved t, you might call it a function of t. Maybe little f of t. If it only involved y, you might call it a function of y. Maybe little f of y. If it happens to involve both t and y, we could still call it a function. How about little f of t comma y? A multivariable calculus function. We're doing a little multivariable calculus while we do our differential equations here. Two inputs to this function. Right? For example, this expression could be 2t plus 3y. That would be an example. That involves both t and y. It could be thought of as a function of both t and y. But wait a minute. Don't functions typically just have one input? I mean, yeah, practically every example you've seen does. But isn't that part of like the definition of a function? Take a given input, give me a unique output. Yes. So how do we get around the fact that it's got two variables there, two inputs? You could think of them as a unit, as a point in the plane. You could think of it as one entity, one point in the plane. And that point can move around the plane. That's important. Slope field for a first order differential equation is of this form, is a graph, as this is hard to describe, is a graph of a bunch of line segments. This is not very precise, whose slope at the point t comma y for many points t comma y is f of t comma y. For many points, or for, you might even say for all points t comma y in the entire plane if the function f of ty is defined over the entire plane, which it may or may not be, though for our examples it will be. It's a little confusing. Let's draw a picture to hopefully dispel the confusion. So here is a plane. Well, it's the paper is a plane. I've imposed a set of axes on the plane. Label the axes t and y. We're typically going to use t for the independent variable here instead of x, because in almost all of our applications, I think maybe all of our applications, the independent variable is time. Though the book sometimes does do examples where the independent variable is labeled x. Don't let it bother you. It's okay to do it either way. So there's my plane. At any given point, say right here, whose coordinates are known, I could call those coordinates just a plane t and a plane y. Maybe that would be a little confusing because t and y are the labels for the axes, are variables. Maybe to emphasize it's a given point, I might call it t sub 1 comma y sub 1. I also could call it t sub 0 comma y sub 0. It doesn't matter what you call it. I'm trying to say it's not necessarily the initial condition. At that point, draw a little line segment with this point as its midpoint. Maybe about like that. And how do you draw the line segment? You choose it so that its slope equals the output of f of ty when you plug in this point as the input. The slope of this slope equals f evaluated at t1 comma y1. In your mind, you can imagine doing this at every point in the plane, infinitely many points. But in practice, nobody can plot such a thing for infinitely many points. So you are satisfied doing it with a certain finite number of points. Though when you're doing it by hand, that gets very tiring. And so maybe you'd restrict yourself to, I don't know, 9 points or something. It's better on a computer. Have the computer plot a bunch of these little line segments. That's what really computers are for, right? Is doing all the grunge work for you. So with this example, the f of ty really just depends on t, not y. I'm going to go ahead and call it f of ty anyway. Even though the right-hand side does not depend on y. Call this f of ty anyway. The dependence on y is trivial. There is no y. It's okay. Doesn't matter. This is the example we just solved. I'd like to make the slope field. If I had to do it by hand, well, what would I do? I'd plug in a bunch of different points into this function, like, for example, 1, 1. T is 1, y is 1. What would I get? I get 0. 1 squared minus 1 is 0. So at the point 1, 1, I'd want to draw a little line segment that's horizontal. Slope of 0. In fact, if t is always 1, it doesn't matter what y is. I'm still going to get a slope of 0 because I only plug in t equals 1. In other words, listen carefully, along the vertical line in the ty plane, watch my hands here, t is horizontal, y is vertical. Along a vertical line where t is 1, just to the right of the y-axis, you're going to make a bunch of little line segments with the same slope of 0. A bunch of horizontal line segments. What if I change t? Like, what if t is 2? Then do 2 squared minus 1, which is not 0, it's 3. And f of 2, 2 would be 3 as well. In fact, at any point where the first coordinate is 2, the output's going to be 3. Meaning, in the slope field, along the vertical line where t is 2, a little further to the right, all your line segments have a slope of 3. What about when t is 0? Do 0 squared minus 1, negative 1. Along the vertical y-axis, where t is 0, all your line segments are going to have a slope of negative 1. Along any vertical line, the slopes are going to be constant. Because along the vertical line, that's where t is constant. Because y doesn't matter. What kind of picture will you get? There we go. Isn't that pretty? Do you have to draw that in your notes? No, don't draw the whole thing, but I would suggest trying to draw it approximately. You won't have to draw all those little line segments, but I would try to draw some of them approximately. And one key thing to get is thinking about those those vertical lines where t is 1 or negative 1, in fact. When t is negative 1, you're also going to get slopes of 0. F of negative 1, 1, for example, is negative 1 squared minus 1 is 0. along these two vertical lines right about here. Make sure you draw this dashed. It's not part of the slope field, really. It's just helping you draw the slope field. And one right about here. I'm going to add in some line segments. You'd want to make those line segments horizontal. Because that's where the right-hand side function has an output of 0 when t is plus or minus 1. Those are two important lines to draw with little horizontal line segments on them. It's the horizontal line segments that are part of the slope field. The vertical lines I drew are not literally part of the slope field. They just help you draw the slope field. Solutions have to follow the slope field. Why? And what do I mean? Anytime a solution passes through the midpoint of one of these line segments, the line segment has to be tangent to the solution, tangent to the curve. And what that means, if you think about it, is that you can draw solutions using that information. For example, one solution, say if I start right about here, it's got to be tangent to that curve, that line segment right there. It's got to be going up about like that, maybe going about through the midpoint of that line segment. And it's got to be concave down because these slopes are getting smaller. It's got to cross t equals -1 with a horizontal tangent. And then the slope has to become negative. It's got to look approximately like this. Will it cross the t-axis there or not? I don't know. I can't draw it perfectly. Doesn't matter much. We're not really focused on that. We're after the shape of the graph. Why does this happen? Remember on Wednesday, I suggested you think of differential equations as talking to you. Don't go crazy with that. It's like you're having a conversation with the differential equation. Hey, differential equation, tell me something. The differential equation doesn't say much. One thing it says is, I am looking for a function whose derivative with respect to t is always equal to this. When I replace y with the function, that's so important what I just said there. I'm looking for a function whose derivative with respect to t is always equal to this expression when y gets replaced by that function of t. These need to be equal for all t. That's easy to think about with pure antiderivative problems. There's a function whose derivative is always the right-hand side, t squared minus 1 for all t. It's harder to think about with examples like the exponential growth model, say dy dt equals 2y. I'm looking for a function whose derivative is always 2 times itself. Y is the function itself. Any constant times e to the 2t is your general solution. Because such functions have derivatives, which I'll just write as y prime here, by the chain rule, always equal to 2 times themselves. That thing is the function. That's one way the differential equation talks to you. A second way the differential equation talks to you, in the equality there, is to say I'm looking for a function of t whose slope at every point, derivative gives you slope, whose slope at any given point, ty on the graph, equals the output of that function at that point. That's the second thing this kind of differential equation says to you. Say it again. I'm looking for a function whose derivative, interpret that geometrically, whose slope, defined precisely as the slope of the tangent line at the point, t comma y, is given by the value of this right-hand side at that same point for all points on the curve. The most important thing, I think, that I just said for the rest of the semester. Understand that. At any given point on a solution curve, imagine its graph. Any point on that graph, the slope of the curve at that point, meaning the slope of its tangent line, is equal to the output of the function, this right-hand side, at that same point. That's why solutions have to follow the slope field. Anytime you go through the midpoint of one of these line segments, because of how we made the line segment to have the right slope of the right-hand side function, that line segment's got to be tangent to the curve. So it's telling you what direction the curve's going. And you can see here, since these things, slope field is constant along vertical lines here, all solutions have to be vertical translations of each other. For this example, they are. It's a pure antiderivative problem. All solutions are vertical translations of each other.